So we got this picture of the atom. You're understanding what the electron is doing. When it absorbs energy, it's jumping up. When it's coming down, it's releasing energy. So how did Bohr convince everyone that he was right and that he could actually calculate the energy levels of an atom? Well, first of all, let's see how he calculated those energy levels, or at least the equation that he came up with. So he used this equation. Energy is equal to negative R sub H. That's the Rydberg constant. So, hey, it's a constant. 1 over Ni squared. So this might look like a weird equation. It's actually a really simple one. You're going to find it to be really, really simple. So this constant right here is 2.18 times 10 to the negative 18th. And note that we're using this version. It's joules. If you Google this constant, you will find it with other units, because some equations, it's better for it to be in other units. But when you find it that way, the number in front will be a little different too, because they've converted units. So this is the R constant that you want to use to solve these equations. And then how do you get to the end? The end is so simple. So if you're talking about on the first energy level, N is 1, the electron that's sitting right there. But if it's bumped up to the second, guess what? N is equal to 2. If it's bumped to the third, N is equal to 3. So that's really easy. So let's just solve for the first energy level's energy. Negative 2.18 times 10 to the minus 18th, 1 over, and then that's just 1. It's on the first energy level. 1 squared equals, so this for the first energy level. Notice it's just basically this number times itself. So that is what our first energy level's electron's energy is. Now let's go ahead and calculate the second energy level. So E is equal to, and I'm just going to go ahead and put the numbers in, negative 2.18 times 10 to the negative 18th, and then 1 over, and now we have 2 squared, because the electron jumped to the second energy level. We just put that in the calculator. Oops. Clear. So negative 2.18 times 10 raised, oh, so I could have used the E key, negative 18th. And then times 1 divided by, you can say 2 squared, or you could also just say 4. I'm just going to put 4 there, because that's what 2 squared is. And that gives us 5.45 times 10 to the minus 19th. Look, that is the energy we have listed for the second energy level. So there's the third, the fourth, the fifth, the sixth. So you want to be able to calculate it yourself. And that doesn't quite explain how he proved that this is what was going on, and how he proved the electrons were all staying in an orbit or a path. So how he proved it was he calculated the energy difference here. So he just subtracted the 5.45 times 10 to the minus 19th. And by the way, that's negative energy, negative joules. And then minus, and then of course there's a negative there, negative 2.18 times 10 to the negative 18th. So that's the first energy level. So he just subtracted the 2, negative 5.45 times 10 raised to the, I don't know why I'm not using the E key today. Maybe so that you can see it. There, yeah, it's intentional. Times, parentheses, negative 2.18 and times 10 raised to the negative 18th. We're going to close that off, and then we get 1.635 times 10 to the negative 18th joules. So that's the energy that the electron would have to release as it was basically jumping between those two, the two positions of this and this. I'm drawing a little short there, but. And so what he did was he calculated, he turned that into wavelength, and he looked at the hydrogen spectrum, and he proved that every time he calculated the different spacings here, each time he did that, it matched with the wavelengths that they had already measured and they already knew that hydrogen had on the spectrum. Remember the bright and pretty colors glowing in the tubes? And they could figure out which different lines that they were? each of his transitions matched with those lines. So everyone was totally happy with his explanation. The only problem is that when they started applying it to atoms that didn't have one electron, his equation didn't exactly work perfectly. And so they had to develop a bigger picture. You might be able to guess why it didn't work perfectly. Maybe it had something to do with the fact that an electron that's negative jumping up or around or near other electrons, there might be some interaction between those two electrons. That might be some additional energy that has to be taken into consideration.